Welcome everybody to Calculus. This is our 1.1 notes section. So we're really going to start to dig in today to determine what is calculus. So it's just going to be a little bit of a preview today. So first off, calculus is the mathematics of change. So we're dealing with math when things don't stay the same. How do we deal with them? And basically it's the reformulation of pre-calculus math through the use of a limit process. So chapter 1 is all about limits, and today we're going to kind of discover why limits are going to be important and how they're going to be used in calculus. So a very fundamental principle, and this is what most of calculus is based on. You can use approximations of increasing accuracy to find an exact answer. So we're going to be doing a lot of approximating today, and as we get closer and closer to the correct answer, we can say what the exact answer is going to be. Alright, so let's explore what we mean by that fundamental principle to estimate the distance on the curve of f of x equals x squared from the point 0, 0 to the point 416. Okay, so what we're trying to do here is find the length of this curve from here to here. Okay, now there's no formula that we know of to do that. The only distance formula we know of is for a straight line. So we can estimate the distance from here to here using that formula, and that's going to be an approximation. So let's go ahead and write out our distance formula here if we can recall it. Remember, it comes from Pythagorean theorem in dealing with right triangles. So we want the difference in the x's, so x2 minus x1 squared, and then plus the difference in the y's, so y2 minus y1 squared. And you can see here a squared plus b squared equals d squared, but then you take the square root of both sides. Okay, so we're going to do this with 2 points, just using 0, 0 and 416. So we really have one distance that we're talking about. Okay, we'll just call this distance 1. Okay, so we're going to apply our distance formula here. And we can use this as our second x, so we want 4 minus 0 squared plus 16 minus 0 squared. Alright, and go ahead and plug this into your calculator here. And we're just going to be looking for an approximation. So when you type this in, you're going to get 16.49. Okay, so that's an approximation. Now, thinking about that, is that an underestimate or an overestimate? Okay, well, the shortest distance between 2 points is 2 lines, and you can see this is a little bit longer. So this is definitely an underestimate. What we can do then is increase the accuracy of this answer by adding more points. And so we're actually going to add the point halfway between 0 and 4 right here. Okay, and so this is the point 2, 4. Now what we get when we do this is 2 line segments. You can see that the approximation is going to be much closer to resembling our line. So in this case, however, we do have to find 2 sections. So here's D2 and D3. So first we need to find the length of D2. You can see it goes from the point 0, 0 to the point 2, 4. So we use our same formula, 2 minus 0 squared plus 4 minus 0 squared. And when we figure this out, let's see, this becomes 4, this becomes 16, so the whole thing is root 20. We'll go ahead and hold off using our calculator just quite yet. and then we also need to find D3. Okay, and that's going to be between points 2, 4 and 4, 16. Okay, so we got 4 minus 2 squared plus 16 minus 4 squared. Okay, so that gives me 4 and 144. So this is going to be the square root of 148. Now, the estimation or approximation is going to be the sum of D2 and D3. So we're going to go ahead and add those up together. And let's go ahead and get the approximation in our calculator here. Okay. Notice this is not the square root of 168. Okay, so you actually have to do each one of these separately and add them together. And here we get 16.64. Okay, so notice it's a little higher than the last one, and we're getting closer. So we can keep increasing our accuracy here. We're actually going to increase it up to 5 points. So we're actually going to split the difference again. So now we're going to have the point 1, 1 and the point 3, 9. And so we can see it, I'll change the color a little bit to this nice purpley color. So we're going to be looking for that distance plus this distance plus this distance plus this distance. Now you can see, even with the pixels on the computer, that this approximation is getting very close to the approximation of the curve. So now we have a few more distances to find. We'll call this D4. This one will be D5. Here would be D6. And D7. Okay, so we actually have to find 4 distances now to find your approximation. Okay, I want you to go ahead and try this on your own. So use your distance formula and come up with an approximation using the 5 points. Go ahead and pause the video, and you can check back to check your answer. All right, so let's check your work here. For D4, we should have gotten square root of 2. For D5, we should have gotten square root of 10. For D6, we should have gotten the square root of 26. And then D7, the square root of 50. And then when you add all those up, you get about 16.75. So you can see our accuracy is increasing as we're increasing our points. Now it turns out that calculus actually yields a specific answer, an exact answer, of 16.8186, and that would be rounded to 4 decimal places. So we can see that our approximation is getting closer and closer to the actual exact answer that calculus will give us. Okay? So let's just make a note here that if we were to keep increasing the number of points, it would increase our accuracy. Now, what we're going to be doing in calculus is we're going to let the number of points go to infinity. And this is where limits are going to be coming into play and why they're going to be so important and why we're spending this chapter talking about limits. All right, so let's move on to our next segment. So there's 2 main branches of calculus. One is differential, The other is integral. We'll just talk about differential for a little bit here. So in differential calculus, we're going to be looking at the slope of a line. It's also called the instantaneous rate of change. We talked about that a little bit before. So to understand this, we need to understand the difference between a secant line and a tangent line. So a secant line is a straight line that intersects a curve in 2 points. So we're just going to draw a curve here. It can really be anything. Okay. Then we're going to draw a secant line, meaning it's going to intersect in 2 points. Okay. So here would be an example of that secant line. And you can see the 2 points here. Now what's great about this is we can find the slope of this line using our good old formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay? And again, this is the change in y over the change in x. So we can find that slope, and we know how to do that. What we're going to be talking about in differential calculus is something called the tangent line. And it's a straight line that just touches a curve at a single point. So the slope of the tangent line and the function at that point are going to be equal. So let's go ahead and draw our curve again. Doesn't really look like anything. And the tangent line is going to come so that it just barely grazes the equation. Okay? And you can see that it's only going to be touching here at a single point. Now the problem here is our slope formula requires 2 points, but now we're only given 1 point. So if we could find the slope of this tangent line, then we can also find the slope of this curve at this exact point. Okay, so let's go ahead and discover how we're going to do this. So the tangent line problem, this is one of the major problems in calculus on which most of what we do in first semester is based on. It says the slope of the secant line through points P and Q as point Q approaches point P nearly equals the slope of the tangent line through point P. So again, we're going to be looking at approximations. So it says using the slope formula m, y2 minus y1 over x2 minus x1, find the slope of a secant line through the points P, C, comma, f of c, and Q, which is c plus delta x, comma, f of c plus delta x. So instead of using x, comma, y, we use c, f of c. So let's go ahead and draw a curve here, and then we can talk about what all of these things mean. Okay, so we'll just draw kind of a parabola-looking thing. And what we want to do is we want to find the slope of this curve right here at this point. Okay. And we're going to say that this here corresponds with an x value of c, meaning the height here would correspond with a y value of f of c. Okay, so there's your x comma y. And we would call this point P, which is c comma f of c. Okay, so what we're going to do here is we're going to let there be some other point, we'll just call it Q, we're going to call this c plus delta x, comma, f of c plus delta x. We'll label it right here. So where did that delta x come from? If we take our first point P, it had an x value of c. So when we go over to point Q, this length is delta x. Okay, so that's where that delta x comes from. And so that's why we get c plus delta x. Okay? And it would correspond right here. So again, here's c, here's plus delta x. That gives us our x value. Now we can also go across right here. The y value then is going to be f of whatever x value this is, which is c plus delta x. Okay, so hopefully you can see where that point is coming from. So what we're going to do is we're going to find the slope of this secant line. Okay, so let's go ahead and find the slope of this secant line right here. So we're using our slope formula right up here. So we have the slope of a secant, m secant, equals, okay, well, y sub 2, which is right here, it's f of c plus delta x, minus y sub 1, which is right here, and that's just f of c, over x sub 2 minus x sub 1. So x sub 2 is right here, c plus delta x, and then minus x sub 1, which is c. All right, we're going to go ahead and clean this up a little bit. In the numerator, we can't really do anything there, so we have f of c plus delta x minus f of c over, well, the c and the minus c cancel out, so all we're left with is delta x. Now, you might have recognized this already from what we did in our preview chapter as the difference quotient. And the difference quotient really is the slope of the secant line through these 2 points. And you can see that there, y2 minus y1 over x2 minus x1, or the change in x. So this is going to be a very important equation as we move forward in the next couple sections. Now, if we think about this, as delta x shrinks, okay, let's think about what happens to this secant line. So as delta x shrinks, it pulls this point closer and closer and closer. Okay? So we can see we might have this point, we might have that point, and eventually it will go until Q is right there with C, and we'll have the slope of our tangent line. Okay? So again, as delta x shrinks, the 2 points get closer. Okay. And here's where the limit comes in. Okay, and the limit as delta x goes to 0, so this difference here goes to 0, actually gives us the slope of the tangent line. Okay. So again, you can definitely see that the limit is going to help us find the slope of that tangent line. For today, however, we're going to be sticking with that idea of differences leading to an approximate answer, and as we get more accurate, we're going to get an actual answer. So, what we're looking for here is to estimate the slope of the tangent line to the graph of f of x equals x squared at the point 1, 1. Okay, so we can see that point right there. And if we were going to draw the tangent line, would look something like that. Okay, so that's what we're looking for, but we're not quite there yet. So we're going to put our point Q1 at 1.5, comma, f of 1.5, okay, which is right here. Okay. So if we find the slope between those 2 points, that's going to give us an approximation for the slope of the tangent line. So to do this, we're going to use our difference quotient. So it's going to be f of c plus delta x. Well, q is already c plus delta x. So we're just going to start off by going f of 1.5 and then minus f of c. Well, c is over here at 1, comma 1. So we'll just call that f of 1. And then on the bottom, we're going to put delta x. So again, remember, delta x is the difference from this x value to this x value. So in this case, it's 1.5 minus 1, or 0.5. So let's go ahead and calculate this out. F of 1.5, this is going to be 1.5 squared, because we're taking it right from this equation right here. And then minus f of 1, so that's going to be 1 squared, over 0.5. Okay. So go ahead and do this in your calculator. Make sure to keep the numerator together. And this is going to give us 2.5. So the slope of this secant line is 2.5. Now what we're going to do is we're going to get even closer. We're going to go where Q2 is 1.1. So we can look here. It's getting pretty close. Call it right there. Okay. So that's the line, secant line that we're looking for. And we just slid that point really close. Now we're only 0.1 away. So we're going to set this up. So f of c plus delta x, that's just 1.1, minus f of c, which is f of 1, over delta x, and we said we're 0.1 away now, so that's our delta x. Okay, so we're just going to go ahead and plug these into our function. We get 1.1 squared minus 1 squared over 0.1. We'll plug this into our calculator, and we get 2.1. Now we're just going to keep doing this process where we're going to get closer and closer to our point C. So now we're only 0.01 away. So we're going to do f of 1.01 minus f of 1. So that's our difference in y's over delta x. And now we're 0.01 away. So we have 1.01 squared minus 1 squared over 0.01. And this is going to equal 2.01. All right, go ahead and find the slope through the point Q4, which now is getting really close. We're 1,000th away. Okay, so we're getting really close to our line. Go ahead and find that, pause the video, and then come back to check your answer. All right, welcome back. So you should have come up with a slope of 2.001. Now, thinking about this, as we've gotten closer and closer, we've let that delta x get smaller and smaller, right? Started here at 0.5, then 0.1, 0.01, 0.001. If we let this dwindle down to 0, okay, where do you see the trend of numbers going towards? Well, hopefully you can see that it's going down, and it's leading us to the number 2. So the slope of our tangent line is going to equal 2. So again, very important that this limit process is going to help us to determine what the slope of the tangent line is. Okay, as we increase our accuracy, we're going to get closer and closer, and then calculus is going to eventually tell us how to find this slope. All right, let's switch gears. Now we're going to talk about the other side of calculus. This is the other half, and this is going to be mostly second semester. This is called integral calculus. It's actually going to be the reverse process of what we were just doing. Now, one of the main problems in integral calculus is something called the area problem. So the limit process can be applied to find the area of a plane region bounded by the graphs of functions. So if we take this nice curve right here and we bound it between these two vertical lines at x equals a and x equals b, and then also with the x-axis, we can actually determine the area under this curve. Okay? So far, before calculus, you could only determine the area of certain plane objects that had mostly straight edges. Now, with calculus, this is the mathematics of change. We can find the area even though this curve is changing over the interval a to b. Now, in thinking about our using approximations, since we can find the area of a rectangle, what we do is we split this area into a bunch of rectangles, all of which we can find the area. So here's A. We'll call this A sub 1, A sub 2, and A sub 3. So when we're looking at this, we could find this area, okay, because we know this rectangle's height would be f of a, because this is the x-coordinate that goes right there. And if we did f of a times the change right here, a to a minus 1, it would give us this area. If we're looking at this rectangle, we know this would be f of a sub 1. So we could take this multiplied by its width, okay, and it would give us the height. And the same thing for the other two rectangles. Now, as we increase the number of rectangles, you can see that this is going to be a much more accurate picture. So here we had a big gap and we were missing quite a bit of the actual area. When we split the rectangles into half, you can see the area that we're missing diminishes. So what we're going to be doing is eventually letting the limit go down so that we have an infinite number of rectangles in here. So we're going to get a very close approximation to the exact answer. And again, calculus is going to help us to do that through the limit process. Okay, so the limit as the number of rectangles increases to infinity is going to give us our exact answer. Okay, so along with this limit is definitely the need to find the width of these rectangles, right? Because it's used in the area. So to find the width, it's always going to be your furthest interval, b, minus your closest interval, divided by n, which is the number of rectangles you're cutting this into. Okay, so if you're cutting into 4 rectangles, you would divide by 4. And we're going to use this here in the next couple examples. So it says, consider the region bounded by the graphs of f of x equals x squared, y equals 0, and x equals 1. So I've shaded the area in here for you. That's what we're looking for. Now we're going to approximate this area first using 4 inscribed rectangle. So inscribed means inside. So when we draw our rectangles, they cannot go above the line, meaning we're going to block it off here. You can see I've already partitioned this into 4 equal sections. So we're going to draw 4 equal rectangles, or of equal width, underneath. So this would be 4 inscribed rectangles. Okay. Now when we do this, we can see that this is going to have an x-coordinate of 0, and if we have 1 here, what's our width? So we always need to be able to find our width. Find our width here. We have our right interval of 1 and our left interval of 0. We're dividing that into 4, and so we get a quarter, or 0.25. So what that means is we're going to start at 0, and then we're going to take our x value at 0.25, and then at 0.5, and then 0.75. Now whenever we do these, we're going to have to find our function values at these 4 points. So we're going to need to find f of 0, f of 0.25, f of 0.5, and f of 0.75. Okay, and you can see our function is just x squared. So 0 squared is 0. 0.25 squared is 0.0625. You can use a calculator. 0.5 squared gives me 0.25. And 0.75 squared is 0.5625. Now what we just did is we found the height of all these rectangles. Now what we're going to do is multiply each one of these heights by the width. So we have 0 times 0.25 plus 0.0625 times 0.25 plus 0.25 times 0.25 plus 0.5625 times 0.25. Now as we go along, you could probably see that you can factor out the 0.25, add up all of your heights first, and then multiply by 0.25. Either way you do that is fine. So we're going to just plug this straight into our calculator, and we're going to sum this up. And it turns out to be 0.21876. Okay, so that's an approximation of the area under the curve, 0.21876. Now another method that's going to help us to do this is using circumscribed circles. So circumscribed is going to be on the outside. So now we're still going to use 4 partitions like we did before, except now we're going to draw the rectangles that are going to be on the outside of the curve. So we actually get this as a rectangle above here, and right here. Okay. Now fortunately for us, now we're going to go ahead and find our heights at 0.25, and then we'll use that for this rectangle. At 0.5, that'll be used for this rectangle. 0.75, that'll be for this rectangle. And then 1 is going to be for this rectangle. Okay, notice our width did not change. It's still 0.25. Okay, so we need f of 0.25, f of 0.5, f of 0.75 and f of 1. All right, we've already found these here from the previous problem, 0.0625, 0.25, 0.5625, and then 1 squared gives us 1. So now we have the heights of each one of these rectangles. We're going to multiply each one by the width. So we have 0.0625 times the width of 0.25 plus 0.25 times 0.25 plus 0.5625 times 0.25 plus 1 times 0.25. And we'll go ahead and plug this into our calculator. And we get 0.46876. Now looking at these, our two estimates are quite a bit different. Okay, and when you do inscribed, this is going to be an under estimate. When you do circumscribed, here you get an over estimate. Now one thing you can do to help make this a little more accurate is to find the average of the two. So you go ahead and add them up and divide by 2. Okay, so it's 0.21876 plus 0.46876 and divide that by 2. And our average would come out to be 0.34376. Okay, so that would be an approximation for the area under the curve. Now, following our theme for today, if we increase the number of rectangles or make that delta x or the width of the rectangles smaller, we're going to get a better approximation. So I want you to go ahead and try this with 5 inscribed rectangles and 5 circumscribed rectangles, and then average the two answers together. Okay, so go ahead and try this on your own. If you need, you can refer back to the notes up here on how to do this. Go ahead and pause the video and then check back when you're done. So, welcome back. Hopefully this wasn't too tedious for you. Should have gotten 0.24 for your inscribed rectangles, and you should have gotten 0.44 for your circumscribed rectangles, and when you average those out, you get 0.34. Now, if we're talking calculus here, what we're going to do is we're going to let n go to infinity. And the n I'm talking about here is the number of rectangles that we're doing this. So the width of the rectangles is going to get very, very small, and we're going to get an infinite amount of rectangles in here, and this is going to give us an exact answer. And it turns out in calculus, the exact answer of this area is going to be 1/3. And you can see here that we got pretty close with our approximation. All right, that's been section 1.1.